We're about to discuss the operating controls and the operation of the 520 Vectorscope. The new Tektronix 520 Vectorscope can be split into two basic operating halves. The right half of the instrument concentrates on measurements. The left-hand side of the instrument concentrates on signal conditioning and signal processing. Let's discuss the signal conditioning portion of the instrument first. The instrument has 10 push buttons on the top part of the signal input portion of the panel. These push buttons are used to select the input signal as well as the mode of operation for the instrument. The two vertical buttons on the far left represent the input to channel A. The top button is the channel A input. The button beneath the input button is for the A calibration circles. Channel B input is on the right side of this 10 push button bank. The channel B calibration circle immediately below the input switch. The center section of 3 push buttons represent on the top the unblanking push buttons. For proper operation, one of these top 3 push buttons must be depressed. Normally, the full field push button is depressed, and the representation on the cathode ray tube is that of a full field of chrominance information. Should vertical interval test signals be in use, we can select the test signal on line 19 or the test signal on line 18, thus blanking out the rest of the chrominance information and making on-air measurements possible by viewing only one line in one specific field. The bottom 3 push buttons represent the phase goniometer selection, and we must also select one of these 3 push buttons for proper instrument use. The A push button refers to the A goniometer. It selects the A goniometer to be used for phase rotation of the input signals. The B phase control does the same operation for the B goniometer. We can select either the A phase or the B phase goniometer for normal operation. If a signal is presented to the, if 2 signals are presented to the instrument whose inherent phase is different, we utilize the time-sharing A phase, B phase alternate push button and thereby utilize both goniometers for the phasing of the signals. Using the A phase, B phase alternate push button, we operate channel A phase goniometer for the signal on channel A, the channel B phase goniometer for the signal on channel B. In normal operation, we must select a signal, and on blanking selection, normally full field, and a selection of a goniometer, perhaps the A phase goniometer. When the push buttons are properly depressed, we then concentrate on the channel gain controls, which appear in the blocks directly below the input push buttons. The channel A block contains the saturation lever switch, which normally is set at 75% saturation, but which may be set for 100% saturation, or for differential gain measurements, the maximum gain position. In addition to the saturation lever switch, we have a thumb wheel control for gain, which can be set for varying input gains. Normally in the calibrated detent position, the instrument is set up for a 1 volt peak-to-peak video signal. The calibrated position then places the vectors on the Vectorscope graticule in the appropriate blocks on the screen. Channel B has an identical block, including the saturation lever switch, the thumb wheel control, and the B-phase goniometer. The appropriate block applies to the input signal being used. To set up the correct gain on either channel A or channel B, 2 screwdriver adjustments are available on the front panel. The screwdriver adjustment B and A set the gain of the individual channels so that the calibrated position will represent a 1-volt full-scale signal. Directly below the gain calibration controls is a phase reference switch with which we select either an external source of subcarrier, plant burst, or an internal source of regenerated burst taken from the input signal as it appears on the cathode ray tube. Directly below the channel gain blocks, we find 5 screwdriver adjustments which can be used for initial setup and after that normally require no adjustment. The top 2 screwdriver adjustments apply directly to the test circles. Quadrature phasing and gain balance ensure that the 2 test circles are properly overlapped and that the circles are indeed circular in nature. Directly below these controls are our clamp position controls. In the vector display, the position is clamped using a DC restorer circuit. It is clamped so that there's no drift from the center of the screen. The horizontal position clamp and vertical position clamp are set on the left-hand side of the instrument with these 2 screwdriver adjustments. The remaining screwdriver adjustment is a beam rotation control which sets the appropriate signal on the screen and adjusts for any misorientation of the cathode ray tube. Normally these controls are not needed and thus the trapdoor can be used to cover them. On the right-hand side of the instrument, beneath another trapdoor, we find additional operating controls. As you can see, these controls are screwdriver adjustments, yet they are screwdriver adjustments of knobs, which imply that these are more operating controls than initial calibration controls. Under the right-hand trapdoor, we find a focus control. Directly below that, the burst flag timing adjustment, which sets the appropriate timing of the internal burst gate so that when sampling the signal's burst, we sample the burst as it occurs on the back porch. We have vertical and horizontal position controls, which differ from the horizontal and vertical clamp position controls in that these controls affect the display in the non-vector displays, the luminance displays. Additionally, we find slide switches to select internal or external sync, and a slide switch which positively selects either field 1 or field 2, especially useful when using the VITS inputs so that we might select the appropriate field for the measurement to be made. Now that we have briefly scanned some of the operating controls of the instrument, why don't we set up the instrument for initial use and then make some measurements. The initial setup of the Vectorscope requires a few minor calibration adjustments. Let's make them now. First, we select the A calibration circle. We must select an unblanking signal and a goniometer for the proper operation of the 520 Vectorscope. Once this has been done, you can see a test circle as it appears on the cathode ray tube. our first adjustment is that of quadrature. The quadrature phasing overlaps the two test circles. As I adjust it, we must adjust for the proper overlap of the two circles. When this is accomplished, a further adjustment of the circles is made using the gain balance control. The gain balance control adjusts the circularity of the circles in the horizontal direction. The best circle is tuned, and after that point, the display is left. After the circles have been properly set, we must set the gain of the individual channels. In the case of channel A, with the lever switch set at 75% saturation, with the gain thumb wheel control set in the calibrated detent position, the amplitude of the circle should be such that it reaches the outer compass circle on the cathode ray tube. The instrument is properly set up, but for demonstration, I will alter the gain of channel A and show the effect on the test circle as I readjust the circle so that its amplitude reaches the outer circle on the graticule. Once this gain is set, we can proceed to make measurements using channel A. An initial setup of the instrument makes it wise to make an additional adjustment to the channel B test circle. And we would do this by depressing the channel B cal and adjusting the gain of channel B. Quadrature and gain balance do not have to be readjusted, as it is the same for both channels. Once the adjustments are made, once these minor checkups have been made, we can close the front panel door, we can select our input signal, and proceed to make measurements using the 520 Vectorscope. As you recall, we selected channel A, a full field presentation, and the A-phase goniometer. Color bars have been applied to channel A. In order to orient them properly on the screen, we use the A-phase goniometer to rotate the display. In the vector mode of operation, the vectors now lie in a conventional color bar pattern with the burst vector on the 180-degree graticule line and the primary and secondary colors being displayed around the vector graticule. The colors as they appear on the graticule can be shown to be within or without FCC specifications and EIA specifications as per the large and small boxes on the graticule itself. The large boxes represent 20 degrees of phase shift and 20% of amplitude change. The small boxes, 2.5 degrees of phase shift and 2.5 IRE units of gain change, amplitude change. Ideally, the dots representing the primary and complementary colors fall within the small squares on the vector graticule. The display we have now represents a single input to the Vectorscope. We have selected channel A. The circle on the screen represents channel B, the calibration signal from channel B. If we wish, we may select a dual trace display, and now we see two signals coming into the Vectorscope. Both of them are color bars, but there's a phase displacement of about 15 degrees between channel A and channel B. In a studio setup, camera timing could be adjusted so that the two signals overlap. The mode of operation that we're using now, using a single goniometer, is such that one goniometer will rotate both signals, and the phase difference between them will remain visible on the screen until the phase of the individual signals is changed. If, on the other hand, the two signals are not adjustable, the phase of the two signals cannot be changed, then a display which is more usable with the vectorscope can be obtained by selecting the alternate phase switch, the A phase, B phase alternate switch, controlling the two A and B phase goniometers. In this case, the A phase goniometer rotates the signal coming in on channel A. It can be set in the appropriate position. The B phase goniometer now rotates the B input signal, and it can be set to overlap the signal on channel A. In this way, two signals whose inherent phase difference is known can be overlapped, and their individual component differences may be measured, assuming that burst vectors have been set to overlap. I might point out that selection of the A phase or the B phase goniometer has no obvious effect on the operation of the instrument. When B phase has been selected, the B phase goniometer operates on both signals. The A phase push button simply indicates that the A phase goniometer rotates both signals. Only when the alternate phase buttons are pushed is there a difference and a time sharing of the two signals. And in this way, phase differences between two signals may be effectively nulled out. We've been looking at a vector display of color bar signals. Sometimes it's advantageous to view the color bars in a slightly different way. Let's see just what we will be doing. If we can look at this small model of the vectorscope graticule, we see, as we look down the end of this clear plastic cylinder, a representation similar to that of the vector graticule. As we look down the cylinder, we can sometimes see the flags that represent the color bars. When we switch to the line sweep presentation, we simply rotate this cylinder, and now we see the composite of chrominance information as it would be seen in a line sweep display. You notice that each one of the color bars appears in the order in which they appear across a conventional picture monitor, yet when we rotate this cylinder, we are in effect rotating the A or B phase goniometer, and as the phase is rotated, the individual vectors rotate with it, and of course change in amplitude according to their angular displacement around the axis. Let's see how this looks on the vectorscope. Here we have the vector presentation. We're looking down the axis of the cylinder. Depressing the line sweep push button, we now see the axis of the cylinder rotated by 90 degrees. When the vectors are originally in the normal mode, with burst along the B minus Y axis, the line sweep mode of operation shows us the line presentation as it is demodulated along the R minus Y axis. You can see that as we rotate the phase controls, the phase goniometers, we're in effect rotating the barrel, and in doing so we are changing the apparent position of each one of the vectors. As we start to use line sweep, we come to the final calibration adjustment in using the 520 vectorscope. The adjustment is burst flag timing. The adjustment is made in the following way. First, we turn down the intensity so just the burst vector is displayed. The burst vector will be intensified in the line sweep position. As we adjust the burst flag timing, the bright spot, the intensification, will move around the burst vector. The proper adjustment of burst flag timing is such that the intensification of the burst vector will fall equally on both sides of the burst vector as displayed in the line sweep presentation. Now that the preliminary adjustments are all completed, why don't we talk about some measurements using the Tektronix 520 Vectorscope. Making measurements with the 520 Vectorscope is enhanced by the operational controls found on the right-hand side of the panel. By depressing the appropriate buttons, measurements such as differential gain and differential phase may be made easily. When using the 520 Vectorscope to set up encoders, several features of the graticule come into play so that easy I and Q gain adjustments may be made. When turning off either of the two I or Q axis channels, the dots fall along the other axis. They either fall along the I axis or along the Q axis. In order to set up the I gain, the Q demodulator is turned off. The dots then appear along the I axis, and tick marks along the I axis on the graticule indicate the location of each one of the colored dots. I gain is then adjusted so that the dots fall on the appropriate spot of the graticule and the I channel is properly set. Setting the Q channel is accomplished in the same way, turning the I axis off and setting the Q gain so that the dots fall on the appropriate portion of the Q axis graticule. When checking the quadrature of I and Q, two different push buttons may be used. If we switch to the line sweep display, which we discussed earlier, you can see that we have the R minus Y channel demodulated, and we can pick out the I and the Q vector from the color bar pattern. If we wish to null out the Q or the I, we simply depress the I push button, and in this case, I is maximized. I is maximized as we are demodulating along the I axis. The Q, being 90 degrees out of phase, is minimized and is at 0. A 90-degree phase shift is accomplished by pressing the Q push button, and now Q is maximized and I goes to 0. This is a very simple and quite an accurate method of checking the quadrature of I and Q. Now let's make some measurements, the typical measurements that are made using a vectorscope: differential phase and differential gain. Because of the nature of our test signal, color bars, it's necessary to utilize still a different test signal for differential gain and phase. The test signal normally used is modulated stair step. Since we don't have a source of modulated stair step available here in the laboratory, but do have vertical interval test signals on our color bar display, we can utilize the VITS push buttons on the 520 and pick out just the modulated stair step, which is occurring on line 19 in field 2. Upon depressing the VITS 19 push button, the only remaining signal on the 520 cathode ray tube is the flickering vertical interval test signal of the modulated stair-step. To make a measurement of differential phase, we simply press the differential phase push button and make the following measurement. By rotating the appropriate goniometer to bring our signal into view on the screen, we can first null out one side of the modulated stair-step. The black side has been nulled out. We bring that point to a null, and then by rotating the calibrated phase control, which has been preset to 0, we null out the other half of the signal. The white end of the signal is now nulled out. When this null occurs, we simply read the calibrated phase control directly. The reading is 2.4, let's say 2.5 degrees of differential phase. This differential phase is present throughout the entire test signal, yet we have utilized the signal that appears only on one line in one field to make this measurement. Using vertical interval test signals, we have made an on-air measurement of differential phase without disturbing the program material. To make a measurement of differential gain, we do the following. First, set the channel gain to maximum. Then select the differential gain push button on the front panel. The signal that we see displayed is an amplitude demodulated signal of the stair-step in the vertical interval. Upon properly positioning the signal on the screen adjacent to the 0% differential gain area on the graticule, we can note the deviation of this signal from 0. The deviation registers approximately 1% of differential gain as read directly on the 520 Vectorscope. The method that we have just used applies to all vectorscopes, assuming that the test signal amplitude, the amplitude of the modulation on each step, is precisely set at 20 IRE units. Some reorientation of the vertical position control on the right side of the instrument is necessary if the deviation is if there is deviation from the 20 IRE level. On newer vectorscopes, later vectorscopes will have a different method for making differential gain measurements, which we will discuss briefly now. We go back to a vector display. We still utilize maximum gain, but in the vector display, we adjust our gain control, our channel gain control, so that the vector reaches the outer compass circle. When this is true, we then press the differential gain push button and make the measurement as we made it before. In readjusting the gain on newer vectorscopes, the position control will not have to be readjusted, and any amplitude stair steps will be able to be used for making accurate differential gain measurements using the 520. An additional feature of the 520 vectorscopes that has not been available on vectorscopes in the past is a luminance channel, the ability to view the luminance information as opposed to strictly the chrominance information as we were able to do in the past. By selecting the Y push button on the measurement side of the instrument, we get a display now that represents the luminance version of color bars. Here we see the descending luminance staircase that represents the descending luminance values of color bars. In utilizing the vectorscope as a luminance measuring device, we have in effect made a waveform monitor out of it. As you see directly below the 520, we have a 529 displaying exactly the same signal in the IRE roll-off position. In addition to strictly luminance information, we are able to also view the output of individual camera tubes. Adjacent to the luminance push button, we have the red, the green, and the blue push buttons, which enable us to view the output of individual camera chains so that we might measure camera channel gain as well. In measuring the output of the red channel, for instance, we know that with proper orientation of the phase control, the first two vectors have red information. The next two do not. The next two have red information, and each one of these indications, each one of these pulses, should be the same amplitude, and we set the red gain accordingly. The green channel as well. The first four color bars include green, and they too should be of the same amplitude if everything was set up properly. The blue alternates with the white flag, the cyan, and so forth across the television line. So that utilizing the luminance channels of the 520 vectorscope, we can view the luminance, the red, the green, and the blue channels of the camera in use at the time. We have just completed the preliminary operation instructions on the Tektronix 520 vectorscope. The nature of this training seminar is brief, and as such, should you have additional questions or measurement problems when using the Tektronix vectorscope, may I urge you to call the local Tektronix field office in the area in which you are operating. There are offices throughout the country, and the local Tektronix field engineer would be most happy to visit with you and help you with your measurement problem.